TOLS, studying in SVC Bengaluru in the branch Electronics and Communication. So today I'm going to discuss Markov analysis and linear algebra. Introduction to Markov chains. A Markov chain is a mathematical system that undergoes transition between a finite or countable number of states. The key property of Markov chains is that the process is memoryless. That is, the probability of transitioning to the next state depends only on the current state, not on the history of previous states. Example: imagine a weather model where the system can be in one of two states, sunny or rainy. The future weather depends only on the current weather, not on past weather. Classification of states in Markov chains. Recurrent versus transient states. Recurrent state. A state is recurrent or persistent if once the process enters this state, it will return to it at some point in the future with probability 1. Transient states. A state is transient if once the process leaves the state, there is a non-zero probability that it will never return. Observing states. As mentioned before, observing states are a special case where once you enter, you remain there forever. Periodic versus aperiodic states. A state is aperiodic if the process can return to the state at irregular intervals. If the system is periodic, it will only return to a state after a fixed number of steps. Ergodic states. A state is ergodic if it is both recurrent and aperiodic, meaning that from that state you can eventually reach any other state with probability 1 and without periodicity. Ergodic chains have unique steady state distributions. Transition matrix. Transition matrix describes the probabilities of moving from one state to another. It is a square matrix where the element Pij represents the probability of moving from state I to state j. If there are n states, then P will be an n into n matrix. The sum of the entries in each row of P must be equal to 1 because the process must transition to one of the possible states. Example: zero point 0.8, zero point 0.2, zero point 4, zero point 6. The first row indicates that from state 1, there is an 80% chance of staying in state 1 and a 20% chance of transitioning to state 2. The second row indicates that from state 2, there is a 40% chance of transitioning to state 1 and a 60% chance of staying in state 2. State vector. The state vector V represents the probability distribution of the system over all possible states at a given time. It is a column vector where each element corresponds to the probability of being in a specific state. Example: if the system has two states, the state vector V might look like 0. 0.7, 0. 0.3. This means there is a 70% chance the system is in state 1 and a 30% chance it is in state 2. The state vector evolves over time by multiplying by the transition matrix. Vt plus 1 is equal to Pvt. This gives the new probability distribution of a one transition. Steady state, stationary distribution. The steady state distribution is a vector that represents the long-term behavior of the Markov chain. Over time, the chain reaches a point where the state probabilities stabilize and no longer change. This happens when the system reaches equilibrium. Mathematically, the steady state vector PV steady is equal to V steady. This means that the state probabilities in the steady states are unchanged by the transition matrix P. Interpretation. The steady state vector gives the long run probabilities of being in each state, regardless of the initial state of the system. Finding the steady state. Solving for the steady state vector. To find the steady state vector, we solve the equation PV steady is equal to V steady. This equivalent to solving the system P minus I into V steady is equal to 0, where I is the identity matrix. The solution to this system is the eigenvector of P corresponding to the eigenvalue 1 since PV steady is equal to V steady. Normalization. After solving for V steady, the elements of this vector are typically normalized so that their sum equals 1. I summation V steady, I is equal to 1. linear algebra interpretation, eigenvalue, and eigenvector approach. A crucial aspect of Markov chain is that their behavior can be analyzed using eigenvalues and eigenvectors of the transition matrix P. The steady-state distribution is the eigenvector corresponding to the eigenvalue lambda is equal to 1. In many cases, Markov chains have a unique steady-state distribution and the system will converge to it after a large number of steps. Observing Markov chains. Observing states. An observing Markov chain is one in which some states are observing, meaning once the system enters these states, it cannot leave. Example, a system where a state represents the end of a process, such as a game that ends when a player wins or loses. Observing chain analysis. In an observing Markov chain, the fundamental matrix N can be used to calculate the expected number of steps to absorption from any observing state. The fundamental matrix is derived from the transition matrix and helps compute the expected time to reach an observing state. Conclusion. Markov chains provide a powerful framework for modeling systems that evolve over time with probabilistic transition. Linear algebra tools, particularly matrices and eigenvectors, allow for efficient analysis and solution of Markov chains. The steady-state distribution describes the long-term behavior of a system, and observing chains have special properties for modeling processes that eventually terminate. Thank you.